privilege to have you, sir. So we have a session taken by Dr. P. Sreehari garu. Before going to the session, I request Mrs. V. Vamsi Sudhira Madam to introduce Dr. P. Sreehari garu to the gathering. Madam.
Respected dignitaries, participants from various colleges, and my dear colleagues, a fine morning to you all. I'm V. Vamsi Sudhira, working as an assistant professor in the Department of ACE. I feel honored to take this opportunity to introduce Dr. Patri Sreehari garu. Dr. Patri Sreehari garu did his BTech in ACE from Nagarjuna University in the year 1991 and ME in Communication Systems from IIT Roorkee in the year 1995. He obtained his doctoral degree in 2011 from National Institute of Technology, Warangal, with his thesis entitled Design of Power Management ICs under Mixed Signal Environment. Dr. P. Sreehari garu started his professional career as a faculty in the Department of ECE in Thapiyar University, Patiala in the year 1995. Later, he joined National Institute of Technology, Warangal as an assistant professor in the year 1999. Currently, he is working as professor in the Department of ECE in National Institute of Technology, Warangal. Dr. P. Sreehari garu is a pioneer in the field of VLSI and communications. He has authored and co-authored several SCI and Scopus indexed journals. He is also working as reviewer for reputed professional journals. He has been the principal investigator for 7 research projects which are funded by MHRD, Ministry of Electronics and Information Technology, MIT, Advanced Numeric Research and Analysis Group, ANURAG, DRDO, and Research Center, IMRAT, RCI, DRDO. He is widely recognized by subject experts around the world, and he even received several awards for his contribution to scientific society. His research areas include analog and mixed signal integrated circuit design, power management ICs, smart SOC design for IoT applications, communication systems, smart sensors, DSP architectures, RFIC design, and SERT circuits. Besides his continuous academic contribution, he also served as faculty advisor for ECE Association in NIT Warangal during 2011 to 2014, and as a faculty advisor for MTech VLSI system design from 2010 to 2016. Currently, he is also serving as vice chairman admissions in NIT Warangal since 2018 and monitoring committee member for E&ICT Academy since October 2011. We are so glad to have you on this occasion, on this auspicious occasion, sir. Thank you for accepting our invitation and being with us. Thank you.
Thank you, madam. Thank you so much. Once again, I welcome Dr. P. Sreehari garu to the session and also thank for accepting our invitation, sir. Sir, now you can start your session, sir. Thank you, sir.
Yeah, thank you very much for the kind introduction. At the outset, I just would like to mention that I'm associate professor, but that's the correction. Now with that, let me try to start my session. So do I have the permission to just now share my screen? Am I audible?
Yes, sir.
Yes, sir, you are audible.
Okay.
Good morning, sir.
Yeah, good morning. Yeah, my screen is visible?
Visible, sir. Right.
Yeah, good morning, one and all.
Good morning, sir.
So, if I'm audible and the screen is visible, I'll try to continue. For the sake of bandwidth constraint, I would like to turn the camera off with your permission.
Sir, your screen is not shared, sir. Now we
Yeah,
can share that.
You can we can see you, sir.
yeah. Is it visible now? Is it visible?
Yes, sir. Yes, sir. Yes, sir.
Yeah. Okay.
Yes.
So, yeah, very good morning. And the topic that is given is basically the significance of the power management integrated circuits, particularly in the mixed signal environment. So this is what is the topic. Let's try to just look at what is the significance of these mixed signal circuits, particularly under low voltage or scale down technologies, and what is the significance of the power management. And subsequently, we will try to move towards specific design issues of the power management within the stipulated time, whatever possible. So let us start with what exactly this mixed signal environment. Though the entire world is moving towards the digital, complete digitalization, but then this sort of mixed signal environment, the significance, of course, we'd like to just see a little bit, and then we'll try to move. Mixed in the sense it's analog and digital together, right? So once you have moved to digital, then why should you want still worry about the analog subsystems is the question, right? So to answer this, we'll try to just look at why we do you need the analog subsystems, and everyone of us are well aware that the naturally available signals are mostly analog in nature. So the innate nature of the signals is analog. Analog in the sense we all are aware that it is continuous with respect to time and amplitude. I just would like to mention that the listeners can feel free to stop me and then pose questions at any point of time if required. And so coming to the significance of these analog subsystems to still accompany, as I mentioned, all the naturally available signals are analog in nature in their innate domain. So what is to be done now? If you want to just now convert them in the name of digitalization, of course, everyone will agree that we need to process the signals in the digital domain because of the advanced state-of-the-art improved algorithms, computationally efficient architectures which are available so that we can process it in an efficient fashion in the digital domain. So one needs to convert the signal into the analog, from analog to the digital domain. But the question here is how quickly you're going to do it once the signal is extracted. So you're going to take the extract the signal using transistors, and this thus extracted signal is, or the acquired signal is generally of very feeble in nature. That is, the amplitude is very, very small. Right. So the examples are just already mentioned there, and such feeble analog signals, they are mentioned in red letters. You can see that they're prohibitively small for direct digitization. Okay, so which implies that if I try to just now sample and quantize upfront, what will happen is they will die down in the presence of concentration noise. The amplitude should be so small. So therefore, it is necessary to first of all to do some processing in its innate domain. What is kind of processing? You make it sufficiently stronger and healthier to be digitized, right? So that means probably you need to condition the signal, maybe filtering, then subsequent amplification. These things are necessary. So if you want to do that, then these filters or the amplifiers obviously should handle the signal in the analog domain, because that's what is the input now. So design of therefore such analog subsystems and then usage of such analog subsystems is mandatory and unavoidable. Okay. Having said this, I just depicted that. No, of course, subsequent to your this sort of processing or signal conditioning, then you are free to just do the data conversion and then process it in the digital domain. No issue. Right. So these are the examples, of course. And having said that, what are the challenges in designing this low voltage circuits, in particular the analog subsystems? Right. Well, why should I speak about the low voltage? Low voltage in the sense, no, all the time we keep speaking about the scale down environment, right? So whenever you are operating with the power supplies, which are much less than 5 volts, now it's 3.3 volts or even 1.8 volts or even now the art of the day is that people are going for sub 1 volt power supplies. When you are using such a very smaller power supplies, what are the challenges? Then one may ask me, why should you go for lower supplies? No, just you said if we think that there is a challenge in dealing with the lower supply voltages, then just operate with higher supply voltage. It might be the easiest solution. But the question here is, everyone will admit that when the technology is scaled down, then we need to scale down the power supply voltage also. Otherwise, what is going to happen? See, the electric field will be enormous, and therefore it leads to breakdown, and therefore we have no alternate but to scale down the technology. Of course, we all are going to be happy with this because we don't need larger voltages, right? So that is it appears on the outset that it's very advantageous. But then under this scale down or environment, then what are the challenges in designing the analog subsystems? Is the question, right? So though the supply voltage is scaled down, but then we want to retain the performance as before, as earlier. We don't want to compromise on the performance. You want to retain same speed. You want to retain all other advantages, right? So if you want to design the circuits with the same performance or better than the circuits which are designed for larger power supplies, then probably what could be the challenges, right? So just start thinking loud. What could be, right? Can just think of. Not only that, and the other one is you need to strive hard to improve the performance also, right? Because the kind of requirement, the exponentially increased thrust towards higher and higher performance. You see now everything is virtual, so you need to have higher and higher bandwidth. Okay, that means higher and higher speed is required. So you need to from one end the performance requirement is increasing. At the same time, we are not able to give the sufficient required voltages or the currents. Okay. So therefore, the need for the analog circuits in the modern mixed signal VLSI achieves, particularly with the multimedia or perception. Otherwise, let's say instrumentation or even medical electronics, or we call it as 5G or beyond or whatever. So definitely, the analog subcircuits are going to play very high a vital role. Okay, so what will be the key limitations that we just now think of? What will be the key limitations? Probably, if you look at, as the supply voltage is being scaled down, one of the first thing that comes to our mind is the threshold voltage also gets scaled down, but it is not in the same proportion as that of the power supply that is being scaled down, right? So as this threshold voltage is not being scaled down the same rate at which the power supply is being scaled down, then what is the challenge? Then immediately we all are well aware that we need to maintain the minimum voltage at the output node, but we want to keep the transistor MOSFET in saturation. We all are well aware. I don't want to go further because you might be aware that we have to operate the MOSFET in the saturation region if you want to do the amplification or any processing in the case of the analog subcircuits, right? In contrast, of course, if you want to use it as a switch, you probably have to use it in the linear region, right? So if you want to operate the saturation region, then you need to maintain that VDS, drain to source voltage of the MOSFET, to be greater than or equal to VGS minus V threshold. This all we know from the fundamentals. So minimum voltage that you are supposed to maintain, and as the threshold voltage is not coming down, then this minimum voltage that you are supposed to maintain at the output node in order to keep the transistor in saturation will be relatively larger only. It is not coming down at the same rate as the power supply. So what this implies? This immediately restricts the maximum possible value of the signal swing. What is the signal swing? Signal swing in the sense, signal probably can go maximum up to VDD, and then at the lower end up to which extent it can go. It cannot go below this VGS minus V threshold, because what is going to happen? Now the transistor will come out of the saturation. So as the supply would see from one end, the VDD is coming down, so therefore maximum possible value of signal is coming down, and at the other end of the signal swing, which is VGS minus V threshold, it is not being pushed down at the same rate as that of the VDD. So the net effect is the available signal swing is very much restricted. Everyone agrees with it? Any contention here? So if you agree with this, then I will just move ahead. What is the other challenge that you can just think of? When you are operating with the scale down technologies, the other challenge from the device that you can just anticipate is the channel length modulation, right? So you presume that the current, of course, when in the saturation region, the current is supposed to be constant against the drain to source voltage. But then due to the channel length modulation, what may happen? This current will not be constant, and indeed it keeps on varying because the length of the channel gets constricted, right? So therefore, this causes the R naught, the output resistance of the device, that's going to be reduced, and then of course, therefore, the amplification possibility is also reduced. So one needs to address this also. Okay, thus that poses further constraint on the minimum length of the device that I can employ, even the technology is scaled down, right? We generally will not, even if it's suppose 45 nanometer technology, we will not use the length to be 45 nanometers in the design of analog circuits. We'll try to use it at least 5 to 10 times the minimum, right, to just take care of this channel length modulation, right? So the bottom line is that even the technology is scaled down, and I'm trying to use the scale down technology, I cannot use or cannot exploit the fullest advantage of scaling down the technology in contrast to the digital counterparts. Okay. And what else? You also might have come across the other artifact as training use barrier lowering, right? And there are many other, scaled down side effects. In addition, probably what you can just think of is as the technology is being scaled down, the all the effects are not 100% probably are not properly modeled, right? So the poor modeling, of course, is another disadvantage that you can just think of. So if it's not properly modeled, all effects are not taken to the device model, then what will happen? Obviously, we just depend upon the model that we have on hand, and we'll try to design the circuit, simulate, and then we bank on our results, and then we send the GDS file to the fab. But then ultimately, the results might be different because the model, our expectation, the way in which the device is supposed to behave is probably being deviated with the practical fabricated device. So that is another thing that you have to just look at. And as I mentioned, signal to noise ratio also is going to be degraded. Why signal to noise ratio is being degraded? Anyone? So, as I already mentioned, the maximum possible value of the signal is already, scaled on because VDD is scaled on, and the other one is uh, signal swing is reduced. And another point, what you can just think of here, very very important point is what is happening to the noise floor. Can anyone think of what is happening to noise floor? What will happen to noise floor? Can anyone just what will the signal to noise ratio now? Because the maximum possible value of the signal is coming down, right? And at the same time, noise flow remains same or it's going to increase because more number of devices are going to be used here, and therefore no, the signal to noise ratio, the situational signal to noise ratio is further exacerbated by the fact that the maximum possible value of signal is reduced and noise flow either remains the same or it's going to be increased, and therefore signal to noise ratio is at stake. In contrast with the digital subsystems, can anyone comment on the signal to noise ratio? Can anyone comment on the signal to noise ratio? See, in the case of digital subsystems, what is the advantage here? In the digital subsystems, simply the decision that is to be taken is either zero or one, either high or low. So there's enough noise margin. Even the logic high is scaled down value or the voltage that is represented, that we are going to use to represent the logic high. Even if it comes down, also there's a big deal, right? Of course, noise margin slightly comes down, but still we can take decision in the favor of either logic high or logic low comfortably, right? So therefore, you can always operate with the scale down technologies as far as digital subsystems are concerned. So you can exploit the scale down technologies to the fullest extent, but that is not the case with the analog subsystems, right? So further, what else you can just think of? Probably, yeah, the voltage, since it is coming down, but as I mentioned in the beginning, the performance is not coming down. We want to increase the performance rather. So when you want to increase the performance or improve the performance, but what you're doing is you're trying to reduce the voltage. So probably you need to consume more current, maybe, therefore more power, right, is going to be dissipated. So you have to now think of architectures which are going to consume less power, right, and but at the same time you are going to give the requisite speed you want to design with the required speed and all. So therefore, these all are the various challenges that you can just think of. Okay, and also, what is the um, maximum possible value of signal generated? Just look at probably if you're using a dual power supply, then this VDD plus modulus of VSS, right? So this should be greater than or equal to what is that? The threshold voltage of the NMOS added to the modulus of threshold voltage of the PMOS. That is a VTN plus modulus of VTP, right? So VDD plus modulus of VSS should be greater than or equal to VTN plus modulus of VTP, right? So therefore, when you're using scale-down technologies, the problem is since the threshold voltage is not being scaled down, then what happens? It results in a decreased on or off resistance ratio, and therefore particularly in the middle of the power supply range, which would normally correspond to the analog ground. So as the process is going to be scaled down, another point is oxide thickness, right? So this oxide thickness, what should happen to oxide thickness in the scale-down technology? Oxide thickness is going to be reduced, right? So as the oxide thickness is going to be reduced, right? So what happens to electric field? The electric field is going to increase, right? So there is a possibility of there is a chance of oxide breakdown as well. So the reduction in the channel length due to this scaling, it also increases, right? What is the reason? Probably with the scale down technology, what is happening? It's becoming tinier and tinier. So the source and the drain are coming closer and closer to each other. So therefore, what happens? The proximity of the source and drain depletion regions, they are going to reduce the effective channeling, right? So therefore, this causes the current to increase heavily, and this probably may lead to irreversible device breakdown, right? So because of this, actually, we are scaling down the power supply voltage, and you have no option. And the power supply is being scaled down, but the question here is, as I said, the threshold voltage is the process dependent parameter, right? So as I mentioned, this is not going to be scaled down proportionately with the process, because the constituents of the threshold voltage, if you look at, they are not going to scale down in direct proportion with the process on the VDD, right? So therefore, these all are the various limitations that you have to just look at, and then hence the design of analog subsystems is going to be pretty challenging, right? Okay, and the adding salt to the injuries, you can just think that maybe generally what happens is, we call them whenever the gain is not sufficient with the single stage, obviously, which is the case, single stage amplifier, how much gain it can give? Probably it may give either 10 or maximum 20 or so. Okay, that is about single transistor amplifier. So when the signal is very, very small, which is the case with our analog subsystems. So we need to amplify it to a larger values. Then what is to be done? Probably you may think, okay, I will use gain boosting techniques. Out of the gain boosting techniques, the most popular happen to be the cascode. So yeah, I'll try to make you the cascode. Why do I go for cascode? Of course, I know that what is the advantage here? Well, first of all, what was the primary disadvantage in using single transistor amplifier? Because Miller effect, no, there will be feedback between the drain and the gate by the virtue of the CGD, right? So this capacitance appears, gain times. So as you try to increase the gain, then the device size increases, the capacitance increases, right? And the amplification, so this capacitance appears gain terms and all, right? So that is going to pose severe limitation on the frequency performance, or the bandwidth is going to be reduced because the pole is going to move towards the origin as you try to increase the gain, right? So this RC 1 by 2 pi RC is the pole, right? So as capacitance is increasing, then of course it moves towards the origin. So therefore the bandwidth is at constant. Therefore I cannot amplify higher frequency signals. So then what is to be done? So probably we have to go for an alternate structure wherein this bearing between the output and input is not there. That means we have to use another transistor between the output node and the drain node of the driving transistor, which is nothing but the cascode transistor. So we go for cascode because of the delinking between the output and the input, particularly the CGD between the output node and the input node is delinked, and therefore simply we will be having beautiful amplification because the output impedance also increases greatly because cascode. So we all know what is cascode and all, but here the problem is in the scale down technologies, the designers cannot use the conventional cascode structures. The reason being, in the cascode, what is the overdrive required? The overdrive required is 2 into VGS minus V threshold, twice the overdrive. Overdrive in the sense minimum voltage that you are supposed to maintain the output. So it is 2 times the VGS minus V threshold, right? So even for a single VGS minus V threshold, we are thinking that my swing is limited. And if you are asking the voltage of the signal voltage of the output node not to go below 2 into VGS minus V threshold, then the signal swing is very much further restricted. So therefore we cannot use this conventional cascode structure. That's another problem here. Right. And what else? The 5th generation applications and all 5G and beyond, they require higher and higher bandwidth. Okay, so we need to think of architectures who can support this. Okay, so further, if you try to look at any other issue with the low power supply voltage, you can just think of probably a person wearing a hefty person, 50 kg person wearing 1 kg hat or weight on his head, and when the technology is scaled down, then they say he becomes feeble, and probably his weight itself is 1.5 kg, and he tries to still weigh the same 1 kg or 900 grams on his head. It's very difficult, So that's what the scenario that you can just think of. Okay, so therefore I already mentioned all the mostly challenges which are related with the low voltage analog circuit design, and so since we cannot use the cascode structures, also we need to just think of alternate structures. Okay, and now we gradually move towards, having said all this, now we will restrict, we will not look at all kinds of challenges with the low voltage environment. We try to restrict ourselves towards the mixed signal environment, and in particular, what are the power management issues. We'll try to just restrict ourselves towards the power management issues. Okay, so what do you think that what are the challenges in particular the mixed signal circuits? So as I said, mixed signals is analog subsystems as well as the digital subsystem, both are there on the same board. Okay, when both are there in the same substrate, then what is the problem? As far as the analog subsystems are concerned, what are the requirements here? The requirements are that I need to maintain signal to noise ratio because I need to just to make the signal stronger, right? I can't afford to use a scale down supply voltage, a very much scaled down technology, and therefore what I will try to do is a relatively higher voltage device I'll try to use. Therefore, a power supply will be higher. Okay, and as far as the digital subsystem is concerned, I can operate it with a lower power supply as well. Okay, so also what is other compatibility issue with the analog and digital subsystem? The nature of the digital subsystem is switching. That is, the output is all the time switching between 1 and 0. Some based on the input signal intelligence variation, output may become either 1 or 0 or vice versa, right? So then what is the since it is continuously switching, what will happen? This switching noise gets coupled with the substrate, and then it appears at the beginning of the or at the input of the analog subsystems, right? So then what will happen? Already analog subsystem receives a feeble, that means very weak analog input. But now this strong, why I call it strong switching noise in this sense? The switching is between VDD and ground. So such a strong switching noise, when it appears at the input of the analog subsystem, the analog subsystem has no way to identify the actual intended analog signal. Rather, it gets succumbed to the whatever the strong switching noise, and therefore simply it malfunctions, right? So this is the biggest disadvantage. So what is to be done? Special measures are to be taken once again in terms of giving good layout design, that is in terms of guard rings or any other measures, so that this sort of isolation is provided between the analog subsystems and the digital subsystems. So there are many other challenges. The noise requirement and then the ground requirements are different. Therefore, all that required is you have to just take additional measures for these mixed signal subsystems. And if you try to look at the entire complex, for example, your mobile itself, it consists of various analog and digital subsystems. As I mentioned, the power supply requirement itself is different for analog and digital subsystems. Therefore, who is going to provide the supply? For all these portable and mobile gadgets, they all are battery driven. When they all are battery driven, then probably you cannot have multiple sources. There's only one battery will be available. When there's only one battery available, but then the power supply requirements for the individual subsystems is very high, right? Let me try to show it here. Yeah. So this is what is the power supply requirement. Okay. So this is see, these all are driven by the lithium-ion battery here, and there are multiple subsystems which have different power supply requirement. You can see this digital voltage island, the power supply requirement is 0.9 to 1.1 volt, and there's a PLL which requires 1.2 volts, and there is a maybe WLAN or RF, probably it requires 2.3 volts or so. So multiple voltage requirements are there. So, but then we all this entire thing, they are driven by single battery, lithium-ion battery. Lithium-ion battery, probably when it is fully charged, it may give a voltage of 4.2 volts. When it is fully discharged, it may give a voltage of 2.8 volts or so. So what is to be done now is there should be an efficient power management system which takes the voltage from the battery and delivers it to the individual subsystems. How? Abstemiously. How much is required? Exactly so much you should not waste the power, because already there's a huge crunch of the power here. So this power management system, once again, it should be part and parcel of mixed signal circuits, and it should provide the voltage to the individual subsystems abstemiously. Okay. Well, another example I can just show you. Here, this is the centralized power management system. So this is going to deliver, power to the individual subsystems, like including the display systems, other digital subsystems, or analog or RF subsystems, and so on. Well, so what is so great about this is the question. Now, under this challenging environment, now we need to design this system in such a way that the overall power that is required to manage or to deliver should be very, very low. Should be, because the name of the power management, we should not again eat away more power. Okay. So, therefore, under these circumstances, what are the challenges that you can just think of? So this implies that you know that when the battery is being we are going to use the battery for powering the device. We try to think of your mobile. What is happening? Morning you're just a charge, but then as you keep on using, very soon whatever you're using a video or any other streaming, whatever, then the battery gets drained out, right? Very quickly it gets drained out. So even as the battery voltage is coming down by the virtue of the usage, throughout the usage, performance should not be at stake, right? And there is also possibility that depending upon the nature of your usage, for example, you try to think of using a flash. When you use a flash, what happens? It requires more current, right? Suddenly, it sucks current. The load sucks current. So that means there is a possibility of sudden load variations, and also the power supply, that means the battery voltage, is also being varied. So against the supply voltage variation or against the load variation, we are supposed to maintain a constant voltage or give a constant voltage to the requisite subsystems. Let them be analog, RF, or digital subsystems. You should deliver them the required voltage irrespective of the battery voltage variations or the load variations. That's what is the regulation. That's what is the regulation, right? So this is the very purpose of a voltage regulator. Now, therefore, we can say that the voltage regulator is helping us to increase the battery life also. Am I right? Because see, we don't want the battery to be charged very often. So that means we should our power management should be intelligent enough in such a way that you try to optimize the battery voltage, right? So to set up the voltage for the sub-circuits that need higher voltage than the battery, then probably, for example, SIM card or backlight LED and so on, then what you have to do is boost converters, right? So if you think that the voltage that I have to supply is less, smaller voltage I have to supply, then I have to step it down. So there's a buck converter I have to use. So these are called DC-DC converters, from DC to another DC. But then either you buck or a boost, or and many times you need to isolate the sensitive circuitry from the transient voltage changes of the battery. So there should be over voltage protection or under voltage protection is also required. This all is the job that is being done by the voltage regulator. Okay, so these voltage regulators, if you look at them, they are broadly can be classified as a linear or switching. Okay, Are you with me?
Yes, sir.
Yeah.
Sir, yes, sir.
Yeah. So, so far what we have seen is that we try to build the case. Why do we? What are the challenges in the scale down environment? In particular, why do we require analog subcircuits, and why do we no go for mixed signal systems? What are the challenges we have seen on the scale down environment? And in particular, why do we go for a sort of a mixed signal, sorry, power management, separate power management unit? This we have seen. Having said that, in that regulation is very, very important. There are many other circuits like voltage, over voltage protection or under voltage protection, right? And many other isolation circuits, but level shifters and so on, out of which we try to focus more of a voltage regulation. So the regulator is fitted to see. We are aware that broadly we can just think of it as linear and switching. So what is the fundamental difference between the, or what are the pros and cons of the linear and switching regulators? Let's look at it. As the name implies, linear regulator says throughout its operation, it's linearly, it means the current continuously flows. Okay, so it is all the time on. This linear regulator is all the time on throughout the regulation. Whereas switching regulator, as name implies, what it does is, yeah, for example, if I want a voltage from 3.6 volts to 2, I want to have 1.8 volts the output. The supply is at 3.6. What I will do, I will try to connect the output node to the battery for some time and disconnect it. That means I'll switch the output node to the battery on and off, on and off. So what happens? If I look at the output voltage here, at the output switch here, this is simply, it just looks like a sort of a rectangular wave, depending upon how much time I'm going to be keep it on. That is how much time I'm going to connect this output node to the battery, and how much time disconnect. So that what happens, I can say that if I do it 50%, that means on time by total time, suppose it is 50%, that means 1/2. That means the average value that I can see at the output of this rectangular wave, but now it becomes square wave here. So it will be simply 3.6/2, 1.8 volts. So in effect, we are able to bring down the supply voltage to a voltage whose average value is 1.8, from 3.6 to 1.8. But the job is not done there, because we don't want this sort of square wave or rectangular wave. We want a constant voltage again. Then I'll use again an LC filter, which will remove this ripple, or if reduces this ripple. I cannot totally eliminate the ripple, but then we'll reduce it by appropriate values of L and C. So I will use an appropriate filter so that I'll get the DC at the output again with the minimum ripple. So this is such a simple switching circuit appears. But then what you have seen, the moral of the story is, by simply switching the output node to the battery or the ground, then we are able to get the output voltage, which is of our required magnitude, right, with appropriate filtering. Well, so now having understood what is the linear and what is switching regulator, Then we'll try to look at some parameters. What will be the parameters here? We try to look at maybe the fundamental thing. The first one, of course, we just think of, because the linear regulator requires the current to flow from supply to the output continuously for regulation. The efficiency is low to medium. Okay. Particularly when the input output difference is very high, then the efficiency is low. Right. That means supply voltage is 3.6 volts, and I want to give an output voltage of 0.8 volts. Now, obviously, difference is so much of voltage you have to drop. No? So that is a poor. It's not efficient, right? And whereas with the switching regulator, the efficiency is very, very high, right? What the reason? Except at very low load currents, where the switch mode quiescent current is usually higher. Otherwise, the efficiency is very, very large. Because after all, I'm just trying to switch here. Only during transitions, there might be slight current flowing. Otherwise, no, there is no power consumption here. Right. So, associated faculties, the heat efficiency, naturally, the waste of the heat, the heat, it will be high. Therefore, use heat sinks and all, right? In the case of linear regulator, whereas in the case of switching regulator, the no, the heat dissipation is very much low. Okay, and what else you can speak of? Probably you may ask me, what about size? What about size? Size in the case of linear regulator, of course, not that. Okay, it's a small to medium in the case of portable designs. But if wherever larger load currents are there, then obviously heat is also there. But heat sinks may take some. It may try to increase the size. In the case of switching regulator, what you can just think of about the size here. The problem is I have used a filter, right? And the switch, two switches I'm using, the PMOS and NMOS. So both of them will be larger, right? And also I've used a big capacitor inductor as a filter. Okay? Therefore, the size might be higher. Further, what you can just think of? Probably very, very, very important point here, the striking difference is the switching noise or the ripple or noise. Right. So linear regulator, there's no question of any ripple here. It's continuous operation, linear operation. So therefore, you're happy that there's no ripple at all. So if any noise is there, some thermal noise and whatever, or flicker noise, which of course there are methods to reduce this or keep them under control. But if you, on the other hand, if you try to just look at the switching regulator, the life itself is switching. So you need to pay special attention towards the ripple. So if you don't design the filter appropriately, the ripple will be very high. So even with the very good filter, you can't avoid the ripple, however small it is. Okay. So these all are the relative merits and demerits that you can just think of. Okay. Having said that, you may just look at which one should I use, right? Linear regulator or this DC converter. I just mentioned buck or LDO. What is it? Buck instance, buck regulator is a switching regulator, and other one is LDO in this sense, low dropout voltage regulator. Okay. So which one do you prefer now? Anyone? So as I mentioned here, switching regulator if you use or buck regulator, at lighter loads, the efficiency is low, right? And these losses, of course, are going to be significant at the low load currents. Okay, so these sort of switching regulator, therefore, you can just think of, because switching noise is going to be very intolerable, particularly for the RF applications. Because in the RF applications, if the switching noise falls within the pass band, then probably it's intolerable, and that will be accepted, right? Therefore, the policy, please just think of this is after all, regulator is giving power to the subsystem. So if there is noise in the supply itself, then say situation is very bad. So, and that too, if that falls within the pass band of the signal that's being processed, then situation is really bad and poor. We cannot assure the requisite signal to noise ratio. So what needs to be done probably is, for baseband applications, we can use this sort of a DC converters, right, or a buck regulator. It is prohibited for RF applications. Okay, and what else? As far as the linear regulator is concerned, what is the major concern here? Continuous current flows, and therefore one may think that, yeah, efficiency might be low, but then the efficiency is low, particularly when the difference between the input and output is very high, right? Otherwise, efficiency is okay, right? So, and the voltage drop, you see in the pass transistor, this voltage drop causes the heat also to be generated. Okay, so you have seen the relative advantage and disadvantage of the buck regulator as well as the linear regulator. Then the question is, see, both have some advantage, both have some disadvantage. How to do? Try to recall Tenali Rama. What Tenali Rama has done? So when he has praised the goddess that she has given, he choose either two facets that she has given, and she asked him to just choose one of the directions, right? So that he can excel in that, or she'll. But he just swallows both the contents of the bowl, so that he wants to excel in both the directions, right? So we want to extract the maximum juice out of the possible plus points. So therefore, what we try to do is, see, when the battery voltage is high, and individual subsystems voltage requirement is low. So if I use linear regulator because I don't want any switching noise and all, but the input output difference is is going to be large. So efficiency is going to be poor. Right. On the other hand, if I only use a DC-DC converter, but the switching noise is going to be there. So to avoid all these unpleasant situations, what we try to do, we use both in such a way that the maximum efficiency is obtained. How? I'll use first DC-DC converter, so that I'll bring down the supply voltage to a value closer to the requisite voltage for the analog subsystem. And then this DC-DC converter buck regulator in tandem with the low drop voltage, or we say linear regulator, when both we use, and what will happen? The input of the linear regulator is now output of the DC-DC converter. So that means the input-output differential is brought down for the linear regulator in a significant fashion, and therefore that will also be efficient. And the added disadvantage here is that the ripple that passes or that is passed by the which regulator it is, the switching regulator will be there as a reminiscent in the supply voltage of the linear regulator. But then there are ways to deal with. If the appropriate design, the appropriate power supply restriction, then we will be able to mitigate the power supply refill. Okay, so therefore the buck regulator in conjunction with the LDO is used for RF applications. Everyone is satisfied with this or not? This question. Any questions at this point?
Sir,
Yeah.
request the participants to express their doubts. Anybody?
Yeah. If there are no further questions, let's try to go ahead. Yeah. So let's try to just spend some time here. Now, gradually we spend the time on the linear regulator and in particular low dropout voltage regulator and the design challenges, and try to just look at some solutions. Okay. So what is the basic idea of the linear regulator here? This is what we might have come across. Um, as the output voltage should be constant against the battery voltage or the load current variations, right? So V naught must be constant, which implies, of course, we can easily say that no, from this analogy or from this analysis, your V naught is equal to R load by R load plus RC to be battery, and therefore RC should be very, very small as compared to R load, right? So, and what is required now is to maintain a constant voltage at the output against the supply or the load variations. There should be a mechanism that intelligently varies this series resistance, see, so that we have a constant voltage at the output, right? That's what the feedback control. Okay, as I shown you the same. So there should be a mechanism. How do you implement this? The question. How do you implement this? Right. So for everything, it's only MOSFET you have to use, right? So this is what is the equivalent circuit here, right? So what we try to do is we'll try to make use of a MOSFET here. So there's a series fast element, right? Now the output is to be sampled, and then we should somehow feed a corrective voltage to the gate of the pass transistor, so that the VGS of the pass transistor is going to vary, which in turn sets right the current as well as the resistance, right? So series resistance also it varies, and therefore you will be finally able to maintain a constant voltage at the output. So this is what the equivalent circuit in the saturation region. So current is a function of ID is equal to half mu C ox W L into VGS multiplication whole square. Beta is mu C ox W L. Okay. Am I audible? I just switch the more.
You're audible, sir. We can hear you.
Right. Now, so this is what in the linear region, simply the resistance varies with the VDS, right? All right. And the transistor regions you might have been introduced by this time. And the MOSFET, when it is in the linear region, the current varies with respect to both VDS as well as VGS. And in the case of a saturation, the current varies only with the VGS, but not with the VDS, right? So that means you can represent it as a constant current source whose current is proportional to VGS square. Indeed, it is a mu C ox W by into VGS minus with the whole square, right? Or simply proportional to mu C ox W by L into VGS square, or I should say it's a beta VGS square. So all that required is intelligently we should be able to vary the gate to source voltage of the pass transistor, or whatever you call this as a series transistor, right? In response to the variations of either the battery voltage or the load variations, we should be able to I'm a lecturer. నేను లెక్చర్లో ఉన్నాను మళ్ళీ మాట్లాడతాను. So this is what is the requirement now. We have to operate the transistor in the saturation region so that it acts as a constant current source, so that I'll be able to exercise control on the requisite maintenance of the output voltage intelligently. If it is now moved to the linear region, what happens is I will be seizing control on the device, because it is now the VDS also varies with respect to the current also varies with respect to VDS, and therefore I will not have much control on the feedback loop. Okay, so well, this is what is the operation of the mass transistor in the saturation region, which we are well aware. Okay, so suppose if the current is the current requirement is in such a way that it's moving from ID2, you can see that is ID2 to ID3, then what happens? Sorry, your slide is not showing. Yeah, so when the current is actually moving from ID2 to ID3, then what is going to happen here? The operating point, you can just see that it is moving from P0 to P2, right? So how is that it's going to happen actually? Because see, as the current is varying now, because it's in the saturation region, what will happen? So we are trying to vary the loop in such a way that the gate to source voltage is going to be increased, so that I can raise the current to the requisite value, right? So in this process, even if VDS varies, there is no big deal here, because it is in saturation, so it will not make any impact of the VDS variations, and only the gate to source voltage variation only will impact so that I can now offer the regulation. That means, so yeah, irrespective of the VDS variation, I'm able to maintain the request constant voltage at the output, but also the required current variation. If it varies from ID2 to ID3, even then I'm able to supply it through the loop variation. Okay, so this is what is whereas in contrast, we try to just move towards a linear region, what's going to happen. So in the linear region, what is your observation here? So when the input voltage is going to decrease to the see, let's look at, instead of load current variation, suppose the supply voltage is being reduced. So as the input voltage is being reduced, what may happen when the input voltage decreases to near the output voltage. See, this is how the x-axis is VDS, which is VI minus V naught. So as VI is being decreased, so this is moving from one operating point to other operating point, right? So as it moves the point, this is the operating point P1, it's moving towards P2 because as VI is decreasing, as it's moving towards P2, what will happen? So beyond this, why it is moving to P2 in the sense, as VI is reduced, then we want to maintain the same load current. In this case, we want to maintain the same load current, but the battery voltage is being drained. As the battery voltage is being drained, but still we want to maintain the same load current, then we will try to vary the gate to source voltage in such a way that it still maintains the same current. That's what is the regulation. We'll try to maintain the gate source voltage. We will vary the gate voltage by taking the by sampling the output voltage, and we will try to increase or decrease the gate voltage, which is depending on the NMOS or PMOS, in such a way that the current is going to be maintained, right? So in this process, VDS varies. Even then, the output voltage remains the same, right? We can keep it same, right? But if the input voltage reduces further, then what may happen? What may happen? As the input voltage reduces further, then you can see that the device is entering into the linear region. This all is a linear region. This all is a linear region. So then as the input voltage decreases further, in the sense, the VGS now, what happens when you try to look at the loop control, when the device is entering into the linear region, now the current is a function of both VGS and VDS. The current is a function of both VGS and VDS. So what will happen? The loop starts seizing its control on the regulation, and therefore the current is now a function of both VDS and VGS. And as VDS changes, so you can see that as VDS changes, then the current also changes. Okay, so as VDS changes, the current also changes, and therefore the required load current might not be met. That is, you are unable to exercise control by varying the requisite VGS here, because VGS now is a fraction of the output sample voltage now, and since device is in the linear region, right? So the regulator loop is going to be cut off, or its role is going to be coming down, right? It will be a function of the input voltage, and therefore if input voltage further reduced, then what happens? It may be further totally the regulation ceases. So the bottom line here is, we can say that we need to operate the device in the saturation, and there is a limit on the range of the input voltage below which the regulation may not happen. The range of input voltage below which the regulation may not happen, which implies that there is a minimum dropout voltage between the input and the output, which you are supposed to maintain, failing which the regulation is not possible. You need to maintain a minimum input output differential to allow the device to, because VDS should be done in VGS minus shown, to allow the device to be in the saturation. Then only you will be able to exercise control on the regulation, right? So having said that, then what is this dropout voltage required? Because obviously we feel that the minimum this dropout voltage, the better will be the efficiency. The minimum this dropout voltage, the better will be the efficiency, because the wastage will be minimum. That's the reason why we now should focus on the design of such voltage regulators which can operate with minimum dropout voltage or low dropout voltage, or you should have control on how much should be this dropout voltage. It should be the circuit should pave the way to reduce this voltage, right, as much as possible, or as much minimum as possible. Hence the name low dropout voltage regulator. Okay, so we will try to move further. This is what I just mentioned here. So so far the device is in saturation, you are able to exercise control because the current is only a function of the VGS, and therefore I'll sample the output voltage and try to vary the gate to source voltage so that I can obtain I can exercise the regulation. And once the device enters the linear region, then as I said, no, the controlling voltage is also a function of the input voltage variation, and therefore the current is also a function of VGS and VDS. Then the regulation becomes poorer and poorer, and at one stage you will not be able to exercise any control, right? So therefore you should try to see that this minimum voltage between the input and the output should be the voltage between the input and output, so that you can exercise control or you keep the device in saturation should be kept as much low as possible. That is the reason why we discuss on, or we just know, or that is the reason why we are going to discuss the low dropout voltage regulators, or we should say this is the justification for the low dropout voltage regulators. So without going further into detail, I just would like to show you how you are going to do it. You are going to sample the output voltage. And why do you need a resistor divider here? The purpose here is that I'm going to use an error amplifier here. So after sampling this, then no, I will try to use a reference, golden reference voltage, which you call it as a band gap reference. I will try to compare with this, because we presume that this is not going to change with the process temperature variations. I will try to compare the sample voltage with respect to that, and we'll try to take a decision in the favor of either decreasing or increasing this gate to source voltage, so that you will try to increase the current if required or decrease the current if required. For example, if the load current, you turn the flash on, you turn the flash on. When you turn the flash on, then you require large current. If you require larger currents, how do you meet? How do you meet the question? So if it's a PMOS transistor, then I will try to reduce the gate to source, or I should say reduce in sense, I'll try to make the gate to source voltage more and more negative, so that more and more current can be pumped here, right? Or if I'm using NMOS transistor, I should try to increase the gate to source voltage or make it more and more positive, so that I can pump more current. That's how it is. Okay. So now, without by taking into account the time constraint, let me try to move towards the parameters here. So what are the parameters for this low dropout voltage regulator? One is the dropout voltage. As I mentioned, there is a difference between the minimum voltage the input DC supply can attain and the regulated output voltage, right? And similarly, input rail range, right? So this is the input supply voltage range that can be regulated. And of course, the lower limit is dependent on the dropout voltage, and the upper limit depends on the process cap voltage, right? And output regulated voltage range, of course, this is the output voltage variation the regulator guarantees. Okay. So when the output voltage is in the range, then we say that, of course, it is said to be in regulation. Well, so further, what else you can just think of is the power supply voltage, power supply rejection, power efficiency, output capacitor range, short circuit current limit, overshoot, undershoot, okay, load regulation, line regulation, output current range, and so on. Out of which we try to broadly categorize the performance into DC and AC, or should say transient parameters, or otherwise DC parameters. DC parameters in sense, and under the standstill condition. So the regulation is the DC parameter,
That means how much what we call against the supply as well as the load current variation, how much variation will be there. So ideally, we presume that this should be zero load variation or otherwise zero, and regulation the value should be as close to zero as possible, right? And as far as the transient response is concerned, what will be the major thing that you're going to observe is if there is a sudden surge in the load current, what will happen? The loop takes some time to respond and deliver this increased current. So meanwhile, the output node bucks, right? The output node voltage bucks, and it is going to suck the current. Okay, so this leads to an overshoot, right? Similarly, if the output current suddenly dips, right, then there will be, what will happen? If there is a sudden dip in the output current, then the output voltage is going to overshoot. So there is an overshoot, and in the previous case, whenever there is a sudden surge in the current, the output node voltage is going to buck. So, and it increases the current. Therefore, there will be undershoot. So whenever there is a load current, sudden surge in the load current, then there will be undershoot, and there will be sudden dip in the load current, then there will be overshoot. So the output voltage, there will be a sudden overshoot or undershoot, and gradually once loop takes the correction or the regulation, then the voltage gets settled back, output voltage will get settled back. But then momentarily there will be overshoot and undershoot. This may damage the sub-circuits or the systems which this regulator is going to drive. So you should be able to protect them, or otherwise you should try to take it as a specification and try to minimize it and keep it well below the permissible values. Now, let's gradually move towards the LDO or low dropout voltage regulator architectures. Okay. So, generally, classification is a conventional linear regulator, okay, which we generally might have already come across. And the other one is the low dropout voltage regulators, right? So let's try to look at what is this conventional linear regulator. So conventional linear voltage regulator, of course, uses a source follower configuration. Okay, so either a single transistor relation or otherwise any other variation also you can use. And let's just look at actually when we are going to pick up any topology, this is called characterization. Okay, this is called characterization. When you try to pick up any topology, we should try to see the merits and demerits of that and suitability of that to the task under consideration. Okay, so actually, what is a voltage regulator? Which kind of output resistance is required? Higher output resistance is required or lower output resistance is required? Which one is required? Obviously, you need to have lower output resistance, right? So lower output resistance is desirable because we don't want the output voltage to change, right? So the lower output resistance is desirable. So can anyone give the justification? Ideal voltage source, right? There's an ideal voltage source. Ideal voltage source should have, what is the internal resistance of the ideal voltage source? It should not drop any voltage, no? Ideal voltage source in sense, मुझे जितना है उतना मुझे देना है बाहर, right? So whatever the voltage, I should be able to make it appear at the output node. So I should not drop, or if it or anything is there, it should be minimal. So the internal resistance should be ideally 0, so that it supplies maximum voltage to the load. So, having observed this, can you please tell me which topology offers low output impedance? Which topology offers low output impedance? Anyone? Of course, it is the source follower. So maybe you can use NMOS. So NMOS source follower is suitable, that exhibits low output impedance. Is it okay? So that's the reason why I have shown you the NMOS source follower. Okay. So this is indeed unconditionally stable. Okay, what will be the output impedance of this topology? Approximately 1 by GM, right? Now, if you try to look at the poles and zeros of this, okay, so yeah, how do you, what will be the dominant pole and what will be the non-dominant pole? What will be dominant pole? Please look at the circuit. What will be dominant pole? See the error amplifier. I think you understood what I said. I'm trying to take the output voltage here. I'm trying to take the feedback from here. Output voltage is V out by R1 plus R2 into R2 is the voltage here. So that I'm going to compare with the set reference and then try to take a decision in favor of either increasing or decreasing the gate voltage. Now, you can simply broadly say there are 2 poles, right? So one pole is probably due to the combination, this combination. What is that? The gate of the pass transistor. This is a transistor called pass transistor. The gate of the pass transistor and the output of this R amplifier node, right? Together, this is one pole. There is one pole. Another pole is at the output here. This is another pole. You can just think of, right? So now these are the 2 major poles here. Out of which one will be dominant is the question. Which one will be the dominant is the question. So this error amplifier output impedance in association with the pass transistor gate capacitance, of course. So that is going to be dominant, and the output node, the pole correspond to the output node, right? In association with the fuse, a large off-chip capacitor here. Here we're going to use large off-chip capacitor because the overstood and understood whatever I mentioned here, they can easily be absorbed by large off-chip capacitor. Large capacitor obviously cannot be on chip. So when you use large capacitor of the order of microfarads, then obviously it should be outside the chip. So this pushes the pole at the output node away from the horizon. Okay. Because 1 by 2 by RC, right? So the source follower output impedance in association with large off-chip capacitor. C is of course large. So, but then source follower output impedance is that. Source follower output impedance, of course, what you have seen. So this in association with this off-chip capacitor, it pushes the pole at the output node away from the horizon. Well, therefore you can see that this pole is dominant pole. It's corresponding to the error amplifier output impedance. This is non-dominant pole. Okay. So the output pole P2 that moves with the load impedance, right? So okay, but of course you can say that's at a much higher frequency. Okay. Now the question here is, all right, we have agreed with the NMOS source follower voltage regulator, but then we need to go for low dropout voltage regulator. So this already have justified that why do we go for low dropout voltage regulator? The what are the major disadvantages of the source follower architecture? Whatever we have seen here. Though we said that beautiful the regulator, in the sense it's a voltage source. The voltage source should offer low internal resistance, and therefore ideally source follower is suitable. But then we want the dropout voltage should be as much as possible. By this time, you are well aware that the dropout voltage input output differential, it is mandatory, no, below which the circuit ceases to regulate. We have already seen, right? So the minimum dropout voltage required for the source follower is what is the minimum dropout voltage for the source follower? It is of course one threshold voltage, right? And also we require one overdrive, right? We have discussed one overdrive, and therefore putting them together, the input of the gate, right? The worst case can be VDD, of course, and if it cannot be VDD, right? Because entire VDD cannot anyhow appear at the gate, right? So therefore the transistor in the output says obviously cannot be the saturation. So it is indeed, of course, it will be a VD set. So therefore, altogether we can put together, say that the minimum dropout voltage in this case is of the order of 1 volt or so, because the threshold voltage is reasonably higher only. So we cannot bring down the dropout voltage much lower by the virtue of a limitation of the source follower topology, right? So obviously, what happens when you don't have control on bringing down the dropout voltage, then this topology is not efficient topology. So one cannot afford to lose power in the name of regulation, right? So therefore, the portable devices which demand longer battery life, and the less the drop across the regulator, the longer is the duration, right? One can use the battery before it succumbs to discharging. Therefore, this mandates low dropout. Okay. Therefore, source follower architecture is ruled out. Okay. Therefore, the bottom line is that the longevity of the battery life mandates low dropout. Okay. Well, if source follower is not suitable, then what else is the question? What is the architecture that is suitable for this low dropout voltage regulator? We'll try to just think of alternates. Okay. Yeah. So, can anyone identify what kind of architecture is this? What kind of architecture is this? This one, you can see the source is common between the input and the output, right? Source is common between the input and the output is the PMOS transistor. Okay, so I'm trying to take a feedback from here and trying to compare with the reference. Okay, and then the output is again driving the pass transistor. Can anyone tell me which kind of topology is this? This topology is? Which kind of topology is this? No answer. Source is common between the input and the output. This is a clue I just now I'm giving. What kind of topology is this? This topology is common source, right? This topology is common source. So the common source architecture, as the output stage minimizes the drop voltage. Here, this is going to minimize the dropout voltage. Therefore, how it is going to do that, you can just see. Probably, if you look at the output voltage, what is the output voltage? It's a V here. Here, VDD minus VDS, right? This is VDD or VN, whatever you call, minus this voltage. That is what is my output voltage. V out is equal to, right? So this VDD minus VDS. Well, so VDS of the pass transistor. So now the question is, I want to reduce this dropout voltage, right? So therefore, that is, I want to make, can I make VDS as low as a few tens of millivolts? Is the question. Can I make VDS as much as low as possible? Any answer? How can I do that? I know the I is equal to half mu C also will be just minus VDS whole square. So if you are able to reduce the VDS as much low as possible, to a value as much low as possible, then the dropout voltage will be as much smaller as possible, right? So can I do that is a question. You can do that. How? By choosing the larger area, right? So this VDS is equal to what? See, I is equal to mu C ox equal to VGS minus V threshold square, right? So this VGS minus V threshold, what is the minimum value of the VDS here? Minimum value of the VDS is nothing but VGS minus V threshold. So this VGS minus V threshold is equal to 2ID by mu C ox WL. So this is the minimum value of the VDS is VGS minus V threshold, right? To keep the transition saturation. So that VGS minus V threshold is equal to 2ID by mu C ox WL. So therefore, I can reduce the VDS by increasing the value of the WL. So the larger the WL I choose, the larger the device size I choose, the smaller can be the drop across it, and therefore I'll be able to maintain lower dropout. That is in my hands now. But the only thing is you have to allow me the area, right? Therefore, this architecture is called low dropout voltage regulator, which permits the dropout voltage to be brought down, and this you can take it as a design specification, and you can always design it for a given or a chosen dropout voltage. Okay, so but then the only limitation is area, because the larger transistor size I have to use. But then not only the area, but the larger the device, what is the added disadvantage here? Another concern that comes to our mind is the larger the device, the larger the capacitances will be CGD and right CDS and CBS and so on. So between the bulk and source and between the gate and drain and between the drain and source and so on, all these capacities will be larger and larger. So if the capacitance is larger, in particular the CG, between the gate and the drain capacitance is very large. So these capacitors, if they are large, then what will happen? CG is large. Then what will be the problem here? The problem is whenever there is a sudden change in the output here, then for example, the load would like to have a sudden surge in the current, right? If there is a sudden surge in the current, for example, in the mobile, I've turned on the flash, then there is a sudden surge in the current. Then who will supply? After all, the battery has to supply the current to the load. Battery has to supply the current to the load. But then, how can I supply the current? This fellow, through regulation, it should sense the requirement, and it should supply. They should change the gate to source voltage. It should make this gate to source voltage more negative so that it can pump the requisite current, right? But because this capacitance is very large, it takes time for this capacitance to charge or discharge, and therefore to effect these changes, it takes time, or the pass transistor is sluggish in nature because of the larger size and hence larger capacitance. So thus, it takes time for this loop to respond to the sudden changes in the load. So that is the disadvantage of choosing a larger size. So obviously, you can just think that major bottleneck or major design challenge happens to be the transient response, or you try to reduce this time. Suppose if we allow so much, you say that, okay, let it take time. Let it take time and respond slowly. What is the problem, you may say? But then, as I mentioned, if there is a sudden surge in the current here, if you are not responding quickly and supplying the requisite current, then what it does is, it is going to, this node is going to buck the voltage and suck the current, right? Or therefore, what happens? Therefore, this sort of there will be an undershoot in the voltage, right? So and similarly overshoot for the other case, and then gradually it will come back, right? But then this sort of overshoot undershoot will damage the circuitry that this the other load that this regulator drives. So we need to restrict these sort of overshoot undershoot. So what generally you do is you try to use a larger capacitance here. What this capacitor does, it just now tries to absorb this this sort of overshoot undershoot, and then simply happily it will not affect the load. But then we are going to see later on that when we don't want any sort of off-chip components. Uh, do you like a big capacitor to be connected outside the PCB or outside for the small device? No, we will not, right? We don't want any such. We want everything to be inside the chip. We don't want anything to be visible outside. It should be as small as possible, and the area also should be minimum. So therefore, everything should be on chip. When you try to make on chip, then the luxury of this capacity, large capacity, will not be there, right? So that you have to keep in mind. Then the challenges will be more and more different and difficult, which we are going to discuss further. Okay. So now for this, I already mentioned that the region of operation should be for the pass transistor, it should be saturation, already given. Okay. And I should actually, when I'm going to design the load that I'm going to consider, of course, is a full load. Under full load conditions, I should design so that even it operates even with the lighter loads also. Okay. So then we gradually move towards stability issues. Okay. So here typically, if you look at the LEO regulators, they use electrostatic resistance, ESR, because when you use off-chip capacitor, it will have its resistance. I can use the ESR, electrostatic resistance of the capacitor, because it is going to give me a 0 as well here, because we have this RC combination that gives me additional 0, right? So we have got P1, that is the dominant pole. And what is the dominant pole here? Can you please tell me here? Here in this case now, because I'm using which kind of circuit? It's not a source follower, rather this is a common source amplifier. So what will be the dominant pole now? Dominant pole is now, anyone? What will be the dominant pole? And what will be the non-dominant pole? Okay, so there are output impedance with the capacitor and of the pass transistor will be dominant, and then of course regulator output impedance with the capacitor is going to be non-dominant. Okay, so quickly let's try to look at here. Of course, this all is this discussion is only making our platform easy, but then we will not use this. Therefore, I will skip this. We will try to move towards the on-chip voltage regulator. Okay. So before going to the on-chip regulator, on-chip LDO, this common source configuration, how much stability is, we'll try to just look at. Okay, so how much stable it is, if you want to see, as I said, no, the dominant pole in this case, because it is it is a dominant pole. You see, in the case of a source follower configuration, the dominant pole happens to be error amplifier output impedance in association with the pass transistor gate capacitance, and non-dominant pole happen to be regulator output node resistance in association with the output capacitance, whatever. So, but in this case, when you try to use common source configuration, in the common source configuration, what will be the pole, configuration of pole composition? The large output capacitor, of course, still we are using. Later on, we are going to remove it. So far, the large output capacitor is there, and the high output impedance, right? High output impedance together, they're going to create a dominant pole P1, right? And the dominant pole, of course, is located in close proximity to the error amplifier output pole. Both are somewhat nearer. And the second pole, as non-dominant pole, is obtained by error amplifier output impedance associated with pass transistor gate capacitance. Because in contrast with the source follower configuration, wherein in the case of source follower configuration, what is that? Because the impedance happen to be very, very low, then the error amplifier output impedance associated with the positive gate capacitance happens to be dominant, and the other one, that is the load pole, happens to be the non-dominant pole in that case. But in this case, this is in the case of common source, the reversal took place because the large output capacitor and the high output impedance, they are going to together, that's 1 by 2 pi RC, right? So that is going to form the dominant pole. Now, as far as the stability is concerned, see, the P1 happens to be pole corresponding to the P1 happens to be pole corresponding to the load pole. So as the load current decreases, the load, the resistance at the output node is going to, see, as load current is going to decrease, the resistance is going to increase. So as the resistance is going to increase, then what will happen? 1 by 2 pi RC. Then as R increases, then the 1 by 2 pi RC is going to decrease, and then it moves away from this pole. Whereas on the other hand, this pole moves towards this non-dominant pole. That means as the load current is going to increase, what will happen? The resistance is going to decrease, right? So 1 by 2 pi RC becomes larger, and this pole moves toward this pole. That means the load current variation is causing this pole, dominant pole, to move back and forth. And as this pole approaches the second pole, then the system becomes unstable. So therefore, load variations are causing this system to be unstable. Okay, so the stability is not guaranteed here. Okay, therefore compensation is necessary. Okay, this is the story of your common source load dropout voltage regulator, but with the large off-chip capacitance. Okay, now as I said, this is not apt for completely on-chip configuration. We're going to move quickly towards on-chip configuration. This is the capacitorless LDO. So, or on-chip LDO. Capacitorless load dropout voltage regulator, in the sense, we want to do away with the large off-chip capacitor, which otherwise is required to mitigate the large overshoots and undershoots, which may arise by the virtue of sudden load variations. So when you just remove that, then we are restricted with the some internal minimum internal capacitance, maximum value 100 picofarads. Generally nowadays people, we are restricting even to the 50 or 40 picofarads, or even less than that. So if that is the case, when you are going to remove the large capacitor at the output node, that means the output node capacitance becomes now a restricted 1 by 2 pi RC. C is now smaller. When C is now smaller, then what should happen to this pole? The pole corresponding to this output node is 1 by 2 pi RC. When C becomes smaller, so 1 by 2 pi RC, C is smaller, then what is the value of 1 by 2 pi RC? That is larger relatively. So therefore, the pole corresponding to this output node should move away from the origin. So therefore, this becomes now non-dominant pole, and the pole corresponding to the error amplifier output impedance in association with the positive gate capacitance now become that will be dominant pole. You understood now why? Again, now we got a swap. See, when you try to consider the source follower configuration, the error amplifier output impedance in association with positive gate capacitance was the dominant pole, and the load pole was the non-dominant pole. And when you have swap changed it towards a common source configuration, then this pole, that is the output node pole, was the dominant pole, and this pole was a non-dominant pole. But now, when you try to remove the large off-chip capacitance, then again the situation has gone back to our earlier conventional case. That is the error amplifier output impedance in association with the positive gate capacitance becomes the dominant pole, and this becomes non-dominant pole. The load pole becomes non-dominant pole. What is the reason? The reason is I have clamped out large off-chip capacitance, 1 by 2 pi RC. C is smaller now relatively, and therefore this corresponding when C is smaller, 1 by 2 pi RC is larger, and therefore this pole is now pushed away from the origin, right? So this becomes a non-dominant pole. Okay, so when it's non-dominant pole, okay, so let's look at this is what is the what is this? This is the pole due to the ramp output impedance in association with the large power sources, gate capacitance, and this is the load pole. Now, what is the implication or what is the impact on the stability? So as the load current varies, as load current is going to move, change. For example, load current becomes smaller. As load current becomes smaller, then corresponding resistance becomes larger. Resistance becomes larger, 1 by 2 by RC becomes smaller. Therefore, this pole moves towards the dominant pole. As load current becomes higher, then the corresponding resistance, load resistance becomes smaller. Therefore, 1 by 2 by RC is larger, and this pole moves away from the dominant pole. That means for higher load currents, this pole is moving away from the dominant pole, and for the lighter load currents or smaller load currents, this pole is moving towards this pole. So now you can just judge which case is more critical, which case is critical, as higher load currents or lower load currents. Higher load currents, this pole is moving away from the dominant pole, and for lighter load currents, this pole is moving towards the dominant pole. Which one will be critical? Obviously, lighter load currents case is the critical one, right? Because this pole, load pole, is moving towards the dominant pole. When it moves towards dominant pole, what will happen? The system becomes unstable, because you know very well that when the poles, each pole is going to contribute how much 90 degrees phase shift, right? So when the two poles are in proximity, there is a possibility that they provide a phase shift of 180 degrees, right? So phase lag, and then what happens is obviously the system or the ramp for our total system gives another 180. But altogether, whenever there's a 360 degrees phase shift is there, then there is a possibility that the Parkinson criterion is met, right? Lubricant phase shift becomes rather than equal to 1, and therefore system becomes unstable. So we want to avoid this situation. This is a challenge here, particularly at a lighter load currents. This system is tending to be unstable. Okay, so you should. This is a big challenge in the case of on-chip low dropout voltage regulator. Okay, so how do you just know counter this situation is the case, and yeah, so we are left with some 10 minutes. This is one challenge. Another challenge, what you can just think of is, I mentioned, these are the actually two poles, actually, if you want for the stability. So therefore, what are the design challenges I mentioned? These are design considerations. One is stability at lighter loads. Load currents is important, and load transient response, which I already mentioned, and power supply rejection. There are the three important design considerations or constants which you have taken into account. Okay, so I already mentioned this. A dominant pole happened to be 1 by R1 into C1 plus CGS plus gain of the pass size multiplied by CGD, because Miller effect, and the pass size is very large, right? The to reduce the VD set. Why did you choose the pass size to be large here? I want to keep the dropout voltage as small as possible, and therefore, the corresponding capacitance will be larger. Therefore, CGS and CGD are extremely large in the terms of picofarads or so. And second pole P2, if you have to see here, is located at the LDO's output here. So the output resistance decreases for the increase in load current. This is all I mentioned. So therefore, P2 is directly proportional to the load current and is load dependent. Okay. So high load current pushes the output pole P2 to the higher frequency, and the capacitance LDO becomes usually stable. But lower load currents, system becomes unstable. We already mentioned this all. So other than this, if you look at the transient response here, so the transient response, of course, I said what is important is this overshoot and undershoot. You are supposed to keep them as much low as possible, because you don't have the luxury of having larger output capacitance. Then the challenge lies in reducing the voltage understood, because see what happened is we have removed the capacitance, but then the pass transistor remains still larger only. Therefore, it is sluggish in responding to the transients in the load, and you need somehow some measures in the topology or the circuital remedies, so that we should be able to reduce the voltage undershoot. And not only that, the settling time also would like to reduce it as much as possible, right? So these are the challenges here. And so this is what I just mentioned here, that the loop is very slow. So what are the ways and means within the 5 minutes or so? Just now quickly mention a couple of solutions here. One probably is try to provide a fast design path, fast path. Fast path in the sense, instead of allowing the loop to respond to the sudden changes here, you try this slow path, right? You try to provide a fast path between, there should be a fast messenger from here to here. So instead of allowing it to be conveyed through the ramp and coming back, rather there should be a fast path between the the output and the gate input here, so that what happens is I'll be able to affect the changes very quickly. The gate voltage will be changed quickly, right? So that the simplest thing is put another capacitor or a differentiator, but then a simple capacitor differentiator again, no, it will have it is a bidirectional one, and therefore I cannot use it as it is. Maybe I have to use a buffer in between, but then I have to just look at the associated stability problems here. So I should be able to do it very wisely, okay, so that it will not affect the pole composition, right? So this is one thing, and that's what we have done the self compensation area. So that obviously is trying to just add zero, all right, that is going to take care of but the zero which I'm going to add here, we should not again hamper with higher load currents where I don't require any compensation. So that is you have to be very careful. That's a design intricacy. And then what else? Of late, there has been a lot of research has taken place, and still a lot of research is going on in terms of what best we can do to improve the performance. Probably, if you try to look at the bassing is adaptive bassing. People started using adaptive bassing. That is the bassing of this the error amplifier which you're going to use. The error amplifier whenever you require larger currents, then you try to provide it adaptively. Whenever you don't require, you can slash down bass current. So this is possible by adaptive bassing. And also another important research output happened to be, if you look at the root cause of the failure or root cause of the problems is larger pass transistor. Why is that you have gone for larger pass transistor? Probably to reduce the dropout voltage. So then when the dropout voltage will be larger, probably when the load current is larger. So when the load current is smaller, then the dropout voltage is smaller. So why do you require larger pass transistor size at lighter load currents? Is not required. But then I have no way to just distinguish between lower load currents and lighter load currents as it appears. And therefore, I'm using single larger pass transistor. So therefore, if you are able to distinguish between lighter load currents and the heavier load currents, then what you do is you try to split this larger pass transistor. Just for the simplest case, use two pass transistors to one is of a smaller size, which can cater to the needs of the lower load currents or the lighter load currents, and a bigger pass transistor to meet to the requirements of a larger load currents. So then what happens is I'll try to switch from one to another, and therefore I need not suffer from larger capacitance associated with the unnecessarily larger pass transistor size. And this concept was further taken, it's taken forward further, and instead of using two transistors, multiple transistors are used like digitization. And then what is done is probably depending upon the magnitude of the load current, the size of the pass transistor is chosen appropriately. So there is a sort of selection circuit, which are multiplexer or selection circuit, which is going to choose appropriate pass transistor based on the current requirement. Therefore, this mandates a current sensing circuit as well. So this is another variation that people have been looking at the from the research viewpoint. And further, what else is we would like to just to make the loop digitized, right? So make it as much digitized circuit as much possible. So the loop is also people are trying to just digitize it. That is, instead of offering a continuous no loop feedback, they're trying to just make it digitized so that I can exploit the advantage of whatever the scale down technologies. Okay, and there is a, as I said, adaptive biasing. When I try to say, then there is a, you can also use a comparator. You can use a comparator which actually tries to allow the whatever the fast path or is not required based on the load requirements. So these all are the various variations which people have been attempted, and indeed my research scholars have worked extensively in this direction, and all this whatever I mentioned my students have done. And then of course a lot of research is going on to design these low drop voltage regulators. And of course we have designed the DC-DC regulator also, that's a buck regulator. And the best bet is use the DC-DC regulator and the low drop voltage regulator in tandem, so that efficiency is improved in a greater extent. And the DC-DC regulator, it should be used upfront and followed by low drop voltage regulator. This is the combination which you're supposed to use. But when you use the DC-DC regulator, you should be very, very careful in terms of the LC, whatever the filter that's going to use, it may be larger. And if you try to reduce the size of that, then there are other design constraints which you are supposed to address, because the magnitude of the ripple may be larger. So you should be, therefore also what is switching frequency you are supposed to use. These all are the various design constraints over there. But having said that, nice designs have come up, and still a lot of research is going in this direction. I should say emphatically that this is one of the most lovable research areas which has a great potential, because whatever is the gadget, whatever is the system that is going to use, power is mandatory. And as I said, there will be analog and digital subsystems, and therefore we need to have a power management, a dedicated power management unit which can do the job efficiently. And challenges are going to be there still, and therefore we need to work more in this direction. And I can just advise somebody is looking forward for the research. This is a potential area that people can still work. Yeah, with this I just would like to conclude, and now the floor is left open for the questions.
Questions from participants?
Any participants? I would can express your doubts. Right, sir. Almost we were at the end of 5-day faculty development program, and we are at the edge of valedictory. So We have our beloved HOD in the convener of the event, Dr. T. Venkateswara garu. Sir, good morning, sir. Good morning,
Good
sir.
morning. Good morning. Am I audible?
Yes, sir, you are audible, sir. I would like to invite you to give a few remarks on this event, sir.
Hello. Thank you, Grishma. Today's chief guest, Sreehari garu, Professor Sreehari garu, and the participants of the event. I'm very happy to see you all, sir. Good afternoon, sir. Sreehari garu. Good afternoon, sir.
Good afternoon.
Really, it is a very good occasion, sir. Thanks for, even though in the pandemic situation, thanks for the online classes and all.
Yeah.
So it is very happy to see you, sir. The most number of the faculty members are now, I think they're enlightened with your talk. And it's really very a good occasion, sir. So this FDP, nearly 103 members are actually registered due to various reasons. So we are having this these topics and all. Thank you, sir. Thank you once again. And I think all the video lectures are available with this video streaming or with YouTube, and it definitely that will be helpful for the faculty. And thank you, sir. Over to Grishma.
Thank you, sir. Thank you so much. Again, I once again thank Dr. Sreehari garu. And I would like to invite you, sir. Sir Sreehari garu, can you give us any remarks on this event? A few words, sir, on this occasion or event, as we are coming to the end of the session.
Yeah. At the outset, I thank TR College and the management and Dr. Venkateswara garu and Dr. Hemlata garu for now inviting me to lecture as a part of your faculty development program. Of course, CR Reddy College is it's always heartening to just know, because it's very one of the pioneering and reputed colleges. And it's always a pleasure to just come up, rise to the occasion, and then deliver lectures as a part of whatever the event that you're going to consider. And in particular, I understand that now the organizers have structured the program so well, and then arranged the speakers beautifully, and so that the requisite topics are covered, and hope that you are going to do several programs in this direction in future as well. Yeah. So with this, also I just thank Miss Grishma and others who are involved in conducting this valedictory as well. And in particular, I congratulate and thank the audience who have been listening to me patiently for the past more than 2 hours, and hope at least some of the insights will be useful in future. I'm open for the discussion any moment. The audience can take my mail ID and they can contact me anytime, whichever is possible discussion. And if it is helpful for you, I can just get ready to move along. Okay. So with this, I once again thank all the organizers, and then so have a good day.
Thank you, sir. Thank you so much. Just inviting us
Grishma.
Lecture, sir.
Grishma. Excuse me, Grishma.
Sir?
Grishma, excuse me.
Grishma,
yes, 1 minute. Can I talk?
Yes, sir. Yes, sir. Please talk, sir.
I am remembering, sir, Sreehari Garu, Professor Garu. Remembering, sir, in 2019, we have an AICT sponsored program. On that day, you are the inaugural guest for the FDP, AICT sponsored FDP, sir. Just I want to make it a memory, sir. That's why I'm take this opportunity. Thank you, sir, Professor Garu.
Thanks for remembering me, sir.
At that day, we are here, sir, for 1 day. I think 2-day sessions are there. So you are here, sir, on that day. I thank our Professor Balaji Garu once again. He suggested the good resource persons for me, and Dr. Professor Rafi Garu, and you and yourself, and Pondicherry from universities, Madam Garu. So it is a really a good effort by my coordinators, Dr. Hemlata and Dr. Madharav Garu, to gather all the eminent persons in a single platform. So sorry for again, I am remember these points. That's why. Thank you, sir. Thank you very much.
Thank you.
Grishma.
Thank you, sir.
Thank you, sir. Thank you so much. That's the point. Actually, I also want to say, sir, I remember that. And really, your collaboration or understanding things are really memorable, sir. And I would like this to continue.
One minute.
Thank you, sir.
Sir,
Thank you so
myself
much.
is I Hemlata.
Now we were at the edge of valedictory, and I would like to invite Dr. I. Hemlata, Madam, the coordinator of this event, to propose a vote of thanks. Madam.
Thank you, madam. Thank you, sir, Professor Sreehari, sir. Sir, really acceptance of your acceptance for as a resource person today's session, sir. Sir, you learn so many things from our lessons, sir. That means regulator, that is a number of types of regulators, how we can regulate that voltages. So that is very useful and helpful for the faculty members who are doing some research work on that one, sir. That is very, very well, sir. Thank you, sir. Thank you very much, sir.
Yeah, thank you. I just would like to add one point. Though the name is Grishma, but the comments and the words are like Vasanta. So, and no, along with Hemalata Garu, really you have made the atmosphere electrifying. Yeah, that's it. Thank you.
Thank you so much, sir. So this is the same word was told by my Telugu teacher, sir, when I was studying 7th class. Really, thanks for your appreciation, sir. Thank you so much.
Overall vote of thanks today. Gratitude should be felt and experienced generously and received graciously. I, Hamlata, stood before you to propose vote of thanks. We have come to the end of 5-day FTP program on recent trends in communications, VLSA and embedded systems. I humbly thank Sri Jasti Mallikarjunudu Garu, correspondent at CRR College of Engineering, for his logistic support. I would like to thank Dr. MBSV Prasad Garu, Secretary Sir CRR Institutions, for his continuous encouragement, and a heartfelt thanks Sri K. Hariram Krishnarao Garu, Management Committee and designated representative, for his endless cooperation. And my sincere thanks to our principal sir for his continuous support. And I express my gratitude to our HOD and convener of the event, Dr. T. Venkateswara Garu, for giving me this opportunity, his support and guidance. And my heartfelt thanks to all the resource persons for their valuable and useful contents to the faculty members. Really, sir, we learned a lot from these 5 days. So many things from your end, sir. And I extended my thanks
to Dr. Tejamurthy sir and my co-coordinators, Dr. C.H. Madara sir and P. Srinivaslu sir, for their support and cooperation. I sincere thanks to participants from various colleges and my colleagues, all my teaching and non-teaching staff for their involvement and cooperation, and also thanks media for support. Thank you one and all. Thank you sir. Thank you very much.
Thank you, ma'am. Thank you so much. So we are almost at the end of the event. And thank you once again for giving me this opportunity. So let us end this session by the national anthem. I would like all the participants to stand for the national anthem, and we'll just close the session. Request all the participants to please for the national anthem.
Let us Chirata Marata Javida Utkalavanga Himachala Yamuna Uchala Jalantarata Tava Shubhanami Jagi Tava Shubhadishamagi Jahi Tava Jaya
जनगणमनोरक जय हे भारत भाग्य विधाता जय हे जय
Jai
हे जय हे जय 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 हे
Jai Hind.
Okay.
I once again thank all the coordinators, HOD sir, and all the session chairs for their involvement, cooperation, and the support. And now we have came to the end of the 5-day FTP program on recent trends on communication, VLSI, and embedded system. Thank you once again for the success of this event, each and everyone, the participants, staff, my colleagues, and everyone. Thank you, sir. Thank you once again, sir. Thank you, sir.
Thank you.
Thank you, sir.
Yeah,
Namaste,
with
sir.
permission, I am leaving it. Yeah.
Namaste.
Yes, sir. Thank you, sir.
Thank you sir. Thank you very much.